Okay, so here we have an NMR spectrum of a compound, and the question is, what is the chemical structure of phenacetin with the molecular formula C10H13NO2? Now we know it's an NMR spectrum because, as well as being told that at the top, notice the range across the bottom, although it's a little difficult to see, goes from 1 up to 7.5 ppm, at least on this scale. It's been cropped down slightly. But also notice that the peaks are split into doublets, quartets and triplets. And on this course we're not splitting in the carbon NMR spectrum, so the scale and the splitting tells you that it's a proton NMR. So using this proton NMR, can we predict the structure of phenacetin with this molecular formula? Well, how do we go about it? Well, the first thing to do is count up the number of different signals in the NMR, major signals. So we have 1, 2, 3, 4, 5, 6. So we have 6 signals, sometimes called peaks. We're ignoring this tiny one here, and we're ignoring these tiny two here. And we can do that confidently because they're much smaller than any other peak in the spectrum. So if we have 6 signals in this NMR, that means we have 6 different environments where a proton exists. So 6 different proton environments. We also have integration to consider, and this first peak here, the integration says 0.8, but in reality we round that to 1. So this small integration line here is for 1 hydrogen. This next peak has integrated to 1.8, but again in reality the numbers are never exact. That is 2 hydrogens. And then you can see the size of the integral lines are roughly similar for this one. So this is 2 hydrogens again, and it's also been integrated to 2.1. The one down here in the middle has integrated to 2.1. So again, that is 2 hydrogens because the integral line is the same height. And then we move on to 2 integral lines which are slightly bigger, and they're bigger by this much. So that means this must be 3 hydrogens, and this must be 3 hydrogens. And again, the computer has integrated this to 3 and this one to 3.2. So we have 6 different proton environments that integrate to 1, 2, 2, 2, 3 and 3. Then we also have splitting to consider. This first peak over on the left hand side is very broad, so we call that a broad singlet because it hasn't split at all. B is a lovely doublet. C is also a doublet. D in the middle here, although it's a little bit fuzzy, is a quartet. This peak E is a singlet, and this peak here is a triplet. So these splittings tell us about what's happening on the neighbouring carbon. Remember, the splitting comes from the n+1 rule, and so it tells us what's happening to the neighbours. And then we also have the chemical shift to consider. Here we have 3 proton environments around 7 ppm. We have a proton environment around 4 ppm, and then we have a proton environment around 2 ppm and one just under 1.5 ppm. So what does that tell you? Well, first of all, let's look at the aromatic region. This region here, between 6 and 8, is the aromatic region. And if you remember from your lectures, if you have these two doublets in the aromatic region, it means that you must have a para-substituted benzene ring. Because this proton here has one neighbour to give you a doublet, and this proton here has one neighbour to give you a doublet. And these two protons are the same. So this one is the same as this one, and this one is the same as this one. So we have symmetry in this molecule. So you see a doublet for these two and a doublet for these two. And looking at the integration, they both integrate to 2 and they're in the aromatic region. So we know we have a para-substituted benzene ring. But we also have this peak here and these 3 peaks here to consider to make up the rest of the molecule. Okay, if you now look at the correlation charts that you were given in lectures, you can see that this peak at 4 ppm, so here at 4 ppm we go up and we can see that it's a carbon attached directly to an oxygen. So here we have an oxygen with a carbon directly attached to it. But notice that this integrates to 2 hydrogens. So in fact this must be a CH2. And also notice that it's split into into a quartet, which means that if the n plus 1 rule equals 4, then n equals 3. So this must be attached to a group with 3 hydrogens on. So this group here, this quartet, is a CH2 attached directly to oxygen because it's at 4 ppm, and it's next to a methyl group because itself is split into a quartet. So if this fragment exists in the molecule, then we must also have a peak for the methyl group. So you'd expect to see something in the alkyl region, which is around 1 to 1.5. And in this case, it will be split into a triplet. And again, looking at the spectrum, at 1.5, we have a triplet which integrates to 3. So we've now been able to assign this methyl group in the molecule and this CH2. So this peak here is a CH3 group attached to a CH2, and here is the CH2 attached to the CH3 and to oxygen because it's at 4 ppm. That now leaves us with this big singlet at 2 ppm and this broad singlet up at 7.5. Well, again, going back to the correlation chart, you can see at 2 ppm we're left with functional groups which have methyl groups attached directly to either a carbonyl or a carbon. So it's these two groups here. So this peak here integrates to 3, so that's the methyl group, and it's attached to either an oxygen or a carbon. But we have oxygen in our molecule. So let's for the time being assume it's oxygen. We can always go back later and change our minds. Okay, so if we count up then our number of carbons, we have 6 in the benzene ring, 7, 8, 9, 10. And we've only got 10 carbons in NMR. So in fact this must be an oxygen, because otherwise we'd have 11 carbons. So now all we need to do is put these two fragments onto our benzene ring in a para-substituted fashion. Well, here we've got an O ethyl group, so we could simply just draw an O ethyl group, which gets rid of these two peaks, this peak, and this one, all in one go. Then we're left with this group here. Now we can't directly attach it to the ring because we have a nitrogen in there. So how about attaching it via nitrogen? Okay, so there is the CO methyl, and there is the nitrogen. So let's look back now at the spectrum to see if our structure fits with what we'd expect. So you'd expect to see two doublets in the aromatic region integrating to 2 each. Yes, we see that. You expect to see a CH2 attached to oxygen, neighbouring a methyl group, and yes, we see a quartet which integrates to 2 at the right chemical shift. We also see the corresponding methyl group right down at 1.5 because it's now just an alkyl chain. It's not attached to any electronegative atoms, and it's split into a triplet as you would expect because it's next to a CH2. Then we have our CH3, which is a singlet, notice, so it has no neighbours, and we have a singlet CH3 with no neighbours. It's also in the right place for a methyl group attached to an sp2 centre. And then finally we have an NH, and we have this proton here, and we also have a proton far down here which integrates to 1 proton. Now this bit is a little bit ambiguous. We can't be sure that this is our NH2, sorry, our NH, but if we did a D2O shake, this proton would exchange for deuterium and this peak would disappear. So we would know we had an exchangeable proton. So all in all, we've come up with a molecule which is structurally sound, and we also have signals which correspond to every peak or signal in the NMR. Now, you may be mistaken for thinking that the structure was something like this. And yes, you would see the same aromatic, 2 doublets, you'd see the NH, you would see a CH2 which splits into 4, and you would see a CH3 which splits into 3 triplet, and you'd also see a methyl group as a singlet. However, this methyl group is directly attached to oxygen, so your 3H singlet should come around 4 ppm, and here your 2H quartet would come around 2 ppm, and it's the wrong way round. Okay, your quartet is actually at 4 and your singlet is at 2, so you know this can't be the correct structure. And that is how you predict the structure from a given proton NMR. Now, obviously you wouldn't rest there, you'd go off and do a carbon NMR as well. And in this particular case, you've still got symmetry, because remember there is rotation around this bond and around this bond. So in terms of the number of carbons you see 1, 2, 3, 4 because they're the same, 5 because they're the same, 6, 7, 8. So in the carbon NMR, you would only see 8 signals. But the fact that your molecular formula says you have 10 means that there is symmetry in your molecule. And then finally, to confirm that you really did have this molecule or this structure, you would do an IR to look for the amide carbonyl stretch, and you would also do a mass spec to see a molecular ion with your molecular formula.